We're going to tie in together all of these identities that we've been working with now and go back to solving trig equations. And now instead of just solving them, uh, simply involving one trig function, there could be more than one trig function, or maybe a higher angle measure in a trig function. So we need to take another look at solving trig equations where we're going to use additional methods to actually find the angle measure values that make the equation a true statement. So let's look at several examples. First, let's solve 4 times the sine squared of x minus 1 equals 0. Here they limit us to 1 revolution around the unit circle. And so it is the difference of two squares. I can see that 2 sine of x plus 1 was multiplied by 2 sine of x minus 1. That gave me the difference of these two squares. So there are my factors. Remember that we solve anything that involves a quadratic-like function. We're going to set each factor equal to 0 and solve for our variable. Here, what we do in trig is we solve for our trig function. So I would set 2 times the sine of x plus 1 equal to 0. I would subtract 1, I would divide by 2, and so that's where this factor solution comes from. And then I would set 2 times the sine of x minus 1 equal to 0. I would add 1 to both sides. I would divide both sides by 2. So there's a couple of steps that they've missed here on this slide, but you can see how we got the sine of x is going to equal negative 1/2 and the sine of x is going to equal positive 1/2. This is where we go back to the unit circle. Sine is negative in quadrants 3 and 4. It is going to be 1/2 at some iteration of pi over 6. That's where the y coordinate is smaller than the x coordinate kind of idea. So we'll get pi over 6, 5 pi over 6, 7 pi over 6, and 11 pi over 6 if we were to list them all in order around the unit circle. But we're going to get 7 pi over 6 and 11 pi over 6 from this factor, and we're going to get pi over 6 and 5 pi over 6 from this factor because we are positive in quadrants 1 and 2 for the sine function. So that's something that we've actually done before. I want you to begin to look for the difference of two squares. It's going to make your work really easy. We see that often in trig functions. So here's another one. It says find the general solutions for tangent squared of x plus 2 tangent x equals negative 1. So we have a squared term, we have a 1-degree term, and we have a constant. So if this was x squared plus 2x equals negative 1, we would know that we had to put everything on the left-hand side of the equal sign, set it equal to 0, and factor what we could. So begin to look at these trig functions as if they were variables in and of themselves. So I see that this can be factored to tangent of x plus 1 times tangent of x plus 1. So we really have one repeated factor. So if I set this factor equal to 0 and solve it for tangent of x, I get the tangent of x equals negative 1. So tangent equals negative 1 at some iteration of pi over 4, and it's going to be negative in either quadrant 2 or quadrant 4. It's where sine and cosine have the same magnitude of square roots of 2 over 2, but where they have the opposite sign in front of them. So that's why we would say x is either 3 pi over 4 or 7 pi over 4. Now let's talk about a general solution when we are not told that we can stop with one revolution. I'll go back to this previous slide. Here it gave us an interval of 1 revolution around the unit circle. Here it does not. It talks about general solutions. Well, because we can keep going and going and going and going around that unit circle, then we have a shortcut way of talking about all of the solutions that are iterations of this one place, this one angle measure on the unit circle. And because tangent has a period of pi, if I multiply its period by a positive integer in the positive direction, then I could say that x would equal 3 pi over 4 plus any k times pi, where k was a positive integer. Now the negative part allows that the general solutions could also involve negative angle measures, so we could go in the opposite direction. So if they ask for general solutions, we first have to pay attention to the period of the function that we're working with. The period for sine and cosine is different than the period for tangent, but the plus or minus k part of it we would take with us for all general solutions. And every mathematician understands that k is going to be some positive integer in this context. So here are the two general solutions for x that make this a true statement, that make this equation true, and that's 3 pi over 4 plus or minus k pi and 7 pi over 4 plus or minus k pi. Let's work some more examples. So if there's more than one trig function involved in the problem, then we're going to use some identities. I could replace one of the trig functions with an identity so that there's only one trig function being used. Here's an example. We have 2 times the cosine squared of x plus the sine of x minus 1 equals 0. So I'm going to choose to replace cosine squared of x using an identity. I don't have an identity that would allow me to replace sine in terms of cosine as a single degree term, but I do have replacements for cosine squared. So I want to put cosine squared in terms of sine. That comes from the Pythagorean identity. It's how come I chose to use this substitution. So I go right here where cosine squared was, and I replace it with 1 minus sine squared. I distribute the 2. That's what I've done in this step right here. And then I put my constants together. So I have negative 2 times the sine squared of x plus the sine of x plus 1 equals 0. I like my lead coefficient to be positive, so I multiply through by negative 1. You can see it changed this sign, and this sign. Now I'm going to attempt to do what I do to solve any quadratic type equation, and that's to find the factors that make it a true statement. So here, this equation factors into 2 times the sine of x plus 1, or sorry, yes, 2 sine of x plus 1 times sine of x minus 1. So I set each one of these factors equal to 0. Here I would subtract 1 and divide by 2. It's how I get this solution. And then here I would just add 1 to both sides, and that's how I get this solution. Again, we're finding general solutions because nothing up here told us to stop within one revolution. We've always just assumed up to this point that we would, because I've never taught you about general solutions up to this point. So we know that sine of x is negative 1/2 in quadrant 3 and in quadrant 4. So that is 7 pi over 6 and 11 pi over 6. We know the period for sine is 2 pi. And again, we have to do that plus or minus k, where k is a positive constant, and that gives us all the solutions all the way up and down the x-axis, along the x-axis for our radian angle measure. So we add that also to 11 pi over 6. We know that the sine of x is positive 1 at the angle measure of pi over 2. And again, for a general solution for sine, we're going to have to add plus or minus 2k pi. So find the general solutions. Now we're back to general solutions. For the sine of 3x plus 2 equals 1. Well, this isn't a single angle measure. This is a triple angle measure. So I'm going to do the same thing that I would do if it was the sine of x plus 2 equals 1. I would take my trig equation and solve it for a single value. And now I'm going to ask myself, the sine of what angle measure equals negative 1? When the angle measure to sine, when sine equals negative 1, the angle measure is 3 pi over 2. That is a quadrantal angle at 3 pi over 2. But instead of setting x to 3 pi over 2, I'm going to set the entire angle measure of 3x to 3 pi over 2. So the sine of what angle measure equals negative 1. So here's my angle measure, and that's where the sine of that angle measure is 3 pi over 2. Now I'm just going to solve for x, so I'm going to divide both sides by 3. And so 3 pi over 2 is 3 pi over 6, which cleans up to pi over 2. And I also have to make sure that the general solution, 2k pi, is divided by that coefficient. So if they ask for a general solution, not only do I put this term, right, not only do I take this term and divide it by the coefficient of x, I need to take that general term and divide it by the coefficient of x. So the solutions that make this a true statement are x equal pi over 2 plus or minus 2/3 k pi. All right, let's do one last solution. Solve 2 cosine of 4x plus the square roots of 3 equals 0. So the same kind of idea. The cosine of my angle measure would equal, if I subtract square roots of 3 and divide both sides by 2, I'm going to get negative square roots of 3 over 2. Cosine is negative in quadrant 2 and in quadrant 3, so quadrant 2 and quadrant 3. It is the larger angle measure, so that's some pi over 6 iteration. So I know that the cosine of the angle measure that equals negative square roots of 3 over 2 is an angle measure of 5 pi over 6 and an angle measure of 7 pi over 6. But now my angle measure is not just x, it's 4 times x. So I need to set 4x, or this angle measure, equal to the angle measure and then divide both sides by 4. Remember as well that I'm dividing 2k pi by 4, which cleans up to k pi over 2. So that's why this doesn't look like 2k pi, because we've already reduced this fraction of 2k pi over 4 to k pi over 2. I divided both sides by 4, so 5 pi over 6 becomes 5 pi over 24, 7 pi over 6 becomes 7 pi over 24. So there we are. There's just solving some more trig equations using different substitutions that we haven't used up to this point. Come to class next time and we'll practice some homework problems.